person, and I want to make a difference in robotics by the application of AI methods. So, the starting point, what I want to after is, I want to go after a challenge by Beetz, who says, so what we should be after is a robot that we can do what we can reasonably expect from it, given what it has as its sensors and effectors. And if you're looking at that, Eric Berger, who was at that time a graduate student at Stanford, I think he makes that vision extremely plastic, illustrative. And so here's a robot, which is a Tier 1 robot, and he carries out activities in an everyday setting. And obviously that is possible, kind of using the robot's actuators. The only little thing that he did was he used remote control. So but for us, that means like, when we study the computation methods, it should be possible to actually substitute the remote control by computer programs. And if you look at current roadmaps and white papers in robotic research, there are things like robotic co-workers, autonomous robot assistants, robot companions, and we should certainly expect, if we have these systems running, they should be able to perform these kinds of activities. We are looking at AI. So AI started very early on in actually looking into these systems. So already in 1917 we had a system, Shaky, which was doing autonomous mobile manipulation and basically started a lot of the whole research field. So what went wrong, which was this perfectly understandable at that time, is that we have started with an integrated system which was very difficult, very expensive to build. And we extracted the reasoning problems out of that system, but then the field started to work on these reasoning problems as they have been extracted by the safety system on its own. So we have fields like knowledge representation, reasoning, uncertainty, planning, learning, vision. All of these fields have their own very competitive conferences. And but if we are looking at putting the puzzle pieces together, we haven't done, I think, as well as we should have done. So I think I like that following lead of it a lot.
My notion pork. Tired dinner unpacked by road. I took 20 days to do.
Hey, Booker?
That, dear lady, is the Wallowitz programmable pen designed for extravehicular repairs on the International Space Station.
Oh, cool.
That's the sweet stuff.
So yeah, I think all of us, or many of us at least, should recognize ourselves when working at complete robot systems in one or the other scene in that. So be kind of that the robots actually move much slower than they should, or that we really have to have in many cases robot behavior for particular instances. And but if we look at more broader in the field, I think we have had in the last years very tremendous success in autonomous systems and intelligent systems that scale real-world tasks. So one example is the Google autonomous vehicle, the Watson system, and also the steering agent, the personal assistant in the iPhone. I think there are only two things I want to remark and not comment on, but I think one is what lessons we have to take is kind of these hallmark developments. They are systems. They are not kind of particular algorithms, but they are complete systems. And if you look inside the system, it will be very difficult to kind of spot particular algorithmic developments where you can really explain the success of the systems based on these particular techniques. And many of the techniques are old. And the other thing is that in the development of all these systems, actually companies played a lot of role, and maybe the cooler academics have terminated a bit wider. So I kind of expect that in the next years we will hopefully see similar things in the context of everyday manipulation, but everyday manipulation is a really, really hard problem. So even if you look at that very simple problem of picking up a particular object from a table, the robot really has to make a lot of decisions. It has to decide on where to stand, which hand to use, how to reach for the object, which grasp type to apply, where to put its finger on the object, how much force to apply, how much lift force, how to lift the object to a particular place, how to hold it. And so that's not enough. So, because all these kinds of decisions, they have to be made in a different way in different task contexts, depending on object states, environment, tasks. So if I take a bottle, in order to put it on the floor, I would take the top of the bottle. If I want to fill a glass, I would have to take the body of the bottle. And so I think a lot of the problems we should really focus on is getting naturalistic task instructions like pick up an object and have an intelligent information processing infrastructure that does the appropriate thing to the appropriate object in the appropriate way in order to satisfy that naturalistic task. Okay, so the kind of thing we are looking into is what I call cognition-enabled control, and the reason that I'm using a little bit different term is that I want to kind of look at the kind of things that we are doing independent of, more or less independent of the methods we are using. So if we look at the very idea of cognition-enabled control, that can be very well illustrated by map-based navigation. In map-based navigation, the idea is that we send the robot around an environment. The robot builds up a model of that environment, and given that model of the environment, the robot can answer queries about the environment. For instance, it can answer the question, where am I? It can answer the question, where is the destination I want to go? And it can answer the question, how do I get from where I am to where I want to be? And if we have that kind of capability in robots to answer these questions, we can write very general control programs in a very compact way. So here we have a navigation routine which gets a navigation task as its argument, and the program code for that is in parallel continually estimate your position. And whenever you're getting lost, you have to relocalize yourself. And whenever you know where you are, you can perform your primary tasks. You can take the tasks that you have, check whether the destination is reachable, compute navigation plan for that, and execute the navigation plan. So what is happening here is we have here a general navigation routine which is very compact, And we can do that because we have embedded reasoning into the control program. So for instance, our control program here does the inference task of position estimation, of actively localizing the robot in the environment, of testing reachability, and of motion planning. And because of that, we can actually build complex control programs that are reliable, flexible, efficiently, and yet have the control programs very compact. So that's basically the idea. And so the way I'm looking at cognition-enabled control is that it should be the information processing infrastructure for decision-making and action parameterization that enables the agent to perform a set of tasks with respect to a given performance measure. And typically we are interested in the generality of the behavior of the system, the flexibility, reliability, and efficiency, and things like that. And it should basically improve that performance of the system based on experience and learning, knowledge and reasoning, and forward models and planning and prediction. And in particular, it is important if we want to have competent action controlling systems that the system is actually capable of reasoning about the consequences of action. So one of the things that I find important is, I think one of the big problems we have is that we haven't understood the problems very well. And so I try to kind of keep out of the definition the method that we are actually using for getting these kinds of systems. Okay, so now I go to my favorite application domain, the housework domain. And so one of the things we were trying is building actually a system that can perform a human-scale task where the instruction for that task is naturalistic, so the way people would formulate the task. We are very interested in something like everyday activities, so things we are kind of typically doing in variations every day. And we find it also important that the systems are actually capable of extending the repertoire of actions and skills that they can have, and using information resources that are intended for human use. Okay, so the scenario we were building was the robot making pancakes. So here we see the system interface. So the system has a semantic environment map, which is essentially a logic knowledge base combined with factors of the environment. We have here a check client where we see the natural language interaction, which is by pattern sentences. Can look at object properties, and here we see the communication of that is happening inside the system, and that is happening in a logic programming language, so where the system varies and responds to the questions that come up in the scenario. So when the system is getting an instruction that it doesn't know of, it looks up web pages like WikiHow, like eHow, where we have natural language instructions about these tasks. So it reads in the instruction we are using the standard parser, kind of building a logic representation out of a triple representation that is compatible with OWL. And then the whole instruction is essentially a set of logic facts out of triples. And then we are building a plan-based control system for that. So that's at the abstract level. And then we have issues of grounding. So for instance, for doing pancake, it needs a pancake mix that was in the instruction. And the question is, how can robots actually know these kinds of things? So in that strawman implementation, what we did is we took a web store that is online in the US and read in all the instructions and mapped them into a taxonomic knowledge base in the research site. So we also had pictures of these objects and we processed them to get SIFT features of these objects. And the SIFT features are then the representation that the robot can actually use to recognize the particular object. So in this case, so it knows it looks for a pancake mix, and then it has to infer where can I look for the pancake mix. And the thing it comes up for, so one of the possible places is a fridge. And the reason it's a fridge is on the left-hand side we have the knowledge of our environment model, where basically we have a fridge as a container object, it's an electrical household, and also in that common ontology we still know that refrigerators are the place where perishable food is kept. And the right part of the taxonomy is actually the taxonomy we extracted from the web store. And by linking these two taxonomies, we can actually take the inferences in that taxonomy built from the web store to our own knowledge and can actually use that as a pointer where to look for the object. So this is basically how we have tried to generate a program for doing that, and now we are coming to the operation side. So we have two robots, and one of them is taking the pick and place task, the other one is taking the actual manipulation. So it's very important for the PR2 robot that does manipulation, the fetch and deliver task that is capable of opening containers, getting objects out of the containers, and delivering them in typical settings. So the settings are still very simple, so we can do more complex than that, but the whole demonstration is so complex that we basically simplify it in order to have not too many source of data. And here we see the robot flipping the pancake, and also many things are kind of implemented still in many ways in a procedural way. All the objects are actually detected, localized autonomously, and the actions are parameterized using the perception data. And the third thing that we are doing in order to kind of avoid that that we have basically hacked a particular system is that we had a phase at the end where we actually asked the robot questions in a logic about what did you see when you performed a certain action, or what did you say then when you were performing the action. So essentially we can ask all of the queries about what the robot did, why it did it, and how it did it. And this is basically by having explicit a data structure, which is essentially a goal tree, and which is basically automatically generated by the log data of the robot performing these activities. Okay, so as I said, so one of the big issues is over-specialization to particular experiment, and so we are pushing and looking at other tasks such as making vice versa sausages, preparing sausages, which is the upper left, place tasks, making sandwiches, going shopping, and so one of the things we wanted to do with these other experiments is as much as possible reusing and adapting the plans that we had for the first demo in order to see whether we can come up with more generalized procedures. Okay, so now I'm going to talk about some of the things that I find are important issues if we look at naturalistic task instructions and robots executing them, and also relate them a little bit to research what is going on in artificial intelligence. So in artificial intelligence, the basic idea is that the robot has goals, and it computes a sequence of actions that provably can get the state that matches the current situation into another state that matches our goal. And so what it should come up with is a sequence of actions. So when we look in the World Wide Web, and also a lot how humans are kind of communicating tasks, they already tell sequences of actions. So if we look at WikiHow, there are individual steps. So there are the steps pour the pancake mix onto the pancake maker and flip the pancake. So, and it's the right order. So what is interesting about these instructions, they are highly incomplete. And so for instance, if you think about, you have the first action pour the pancake mix onto the oven, and the next action is flip the pancake. The system has, first of all, to recognize that the pancake mix is becoming a pancake. So that it's actually kind of the same object. The other thing is, the instruction doesn't say anything that the pancake maker has to be switched on. So the system has to infer, in order to have a pancake later that I can flip, I actually have to switch on the oven and wait until it's done. So these are kind of the kinds of inferences that we expect the system, an intelligent action execution system, needs the capability to perform. And this is very much in contrast of what AI planning is doing, because here we have the sequences of action. So the question here is actually extracting the goals from the individual plan steps, because we want to perform the actions much more generally and much more flexibly than described in that. So these are, I think, important computation problems that we have to focus on. So let's take a step down and look at individual actions. So one of the actions is push the spatula under the pancake. So if we want to perform that with a robot, we shouldn't actually perform that literally and try to push the whole spatula under the pancake. So if we have an instruction like that, so we have to look what is meant with such an instruction. So what is meant is, so what we have to come up with, we have as input a naturalistic action description, which is kind of very vague, very ambiguous, and very incomplete. And we have to come up with something that is more like an effective action specification. And the effective action specification should say something like, you have to hold the handle of the spatula and push the blade of the spatula under the pancake, and you should push the blade under the pancake such that you can lift the pancake safely, such that you don't damage the pancake and you don't push the pancake off the oven. So that's, again, the style of reasoning we need at that particular level. And if we are going yet another step down, and we are looking at the individual actions, namely pushing a spatula under the pancake, the other thing is that actually, unlike in artificial intelligence, where we abstractly assume there are preconditions, and if the preconditions are satisfied, then the actions will work. Here, the effects of the actions, they heavily depend on how the movement is executed. That we actually kind of have the right angle of the spatula, that we have the right force to get under the pancake. And one of the big problems that I see is that in artificial intelligence, so we so far don't have the concept of motion, of movement explicit, and if you want to actually kind of solve these kinds of tasks, the AI system has to talk about how movements have to be executed. Okay, so let's switch to some of the principles that we have adopted to realize our control system. So the core are 3 principles, and the first principle is that the control program that we are talking about, it's not a sequence of actions. It is a concurrent percept-guided control program. And the control program actually specifies how the robot is to respond to perceptual events, to success and failure, in order to accomplish its tasks successfully. So in our idea, we have the assumption that actually sequences of actions are just a story that an agent tells itself in order to make computation problems practical. But that sequences itself are not expressive enough to actually get the kind of competence in behavior that we need. So the second principle I already talked about is that if we are looking inside that concurrent reactive control program that specifies the behavior of the robot, so we have control decisions that the system is made, and the control decisions have to be derived by inference. So we want to separate kind of, so we want to have statements like do the action appropriately, and then the system reasons about what does it mean to perform the action appropriately in that particular context. And the third principle is that if we are looking at that concurrent reactive control program, so we want to have that concurrent reactive control program as an explicit declarative data structure that the robot can actually look at execution time. So for us, so basically the plan is not something that is constrained by a syntactic language, but it's actually the system that is executed on the system, and it's only the part that is made explicit of that. Okay, just some remarks about the control program, but I want to focus more on inference parts. So yeah, as I said, the robot control programs specify how to respond to the sets and events, in particular failures to accomplish its goals. And so the way we are in that spectrum between for robot control can be contrasted to the traditional AI approach. So in the traditional AI approach, we make the basic assumptions. Plans are partially ordered set of plan steps, that actions have preconditions. Robots have to reason about all the plans that are actually expressible in that language. They have to generate provable correct plans, or in some formulations optimal plans, or in others the most robust plans. And they assume a single query property. So it gets a task, has to compute the plan, and executes the plan, and then forgets about that it ever has solved the task. So in our control framework, we phrase that computation task a lot differently. So we are kind of losing particular assumptions, but making other assumptions stronger in order to keep the computation problems tractable. So yeah, I already stressed the point, plans for us are concurrent reactive control programs. Another thing is, in our, when we have libraries of action plans, but our action plans are actually more universal. So they get rid of preconditions. They handle all the typical context situations. And so if a robot is to grasp an object, and it has an object in the hand. It puts down the object and basically grasps the object. So what is the big advantage of that? If we have actually action plans that are universal in that sense, the robot planning system can actually perform, can insert that action at any time, at any place in the plan, and that plan would at least work locally. There might be negative interactions between other parts of the plan, but in itself it's at least executable. And the other assumption that, so in classical AI, we make the assumption that we have to generate all plans that are expressible in a certain language. And we know that there is a general trade-off between the expressibility of the language and the tractability of the reasoning problems. And so what's happening is that typically in AI planning, we have these syntactic languages which are forced to be very simplistic, and the reason is that we have to keep the computation problems of generating these plans tractable. In our system, we make another assumption. We make the assumption that the plan language is defined in an operational way. So that means the only plans that the robot has to reason about are the plans that are atomic in its plan library, the plans that it generates by composing these actions, and the plans that are revisions of these plans. So by defining that way, we can have a very expressive language, like including concurrency, event-drivenness. But still, we can design the plans that they are easy to reason about. So they can, for instance, mention all the goals they are achieving and so on. Okay, instead of provably correct the plans, we are only interested in improving expected performance, and instead of having single query planning, we are actually exploiting the everyday manipulation property of the world, that most of the plans can be reused, and even if we have failures sometimes, and we learn from these failures, kind of the amortized behavior over the future will still be outperform anything that is done. Okay, so I want to now look at some of the inference tasks that we are looking into, and where we think that they could become part of realizing smarter robotic systems. So again, if we are looking at household tasks, so the way we would like to write our plans are, we have the task clean up, and we would write the plan like, for each object on the table, do put the object where it belongs, or set the table, and for each object that is needed for the breakfast, put the object where it belongs. So again, kind of we have the reasoning problems. Given the evidence that we have, for instance, that Peter and Mary are having breakfast, but they are in a hurry, we have to infer what will they most likely eat, when they eat, what will they need as utensils, and then put those objects in the right spatial configuration on the table. So we believe that these inference tasks are much too complex, too varied, and too strongly affected by uncertainty, by real-time constraints, by real-world conditions, to be addressed by a general-purpose reasoning mechanism. So rather we kind of look at doing the different subtasks of reasoning in whatever reasoning mechanism is most appropriate for the particular task. So if we are looking at where we want to put down an object, and in a particular constellation where we want to take into account the current position of the robot and an expected future location of the robot, and so we want to find a place that is reachable from both locations, that is a stable position for the object, and visible from the future expected location, then we can specify all of like laws like that. But so if we are asking for the target position of the robot, the best place to look it up is the control program itself, right? So where the position estimate is done. If we are thinking about whether when we put the car at a particular place and whether it's stable, the best method we can use for checking that is doing a short physical simulation. If we want to check whether whether a particular place is reachable, the best thing we can do is, or kind of one heuristic that we are doing is using the inverse kinematics of the robot. And if we want to check visibility, so we can use some of the graphics engine like OpenGL in order to realize those things. So, so what we have in our framework is that at the third layer here, we have a set of order parameters. And above that, in the control program, we have the control programs have a uniform framework, namely order, to actually answer that queries. But if we look at the bottom layer, we have kind of the best reasoning mechanisms that we can think of in order to realize the corresponding predictions. So that's the idea. So one example for inference method 1 is whether a task is a subtask of another one. And so we have predicate, all predicate subtask, which takes two tasks as arguments, which might be specified for variables. But in order to realize that predicate, we are actually looking at the execution stack of the program and execution time using a predicate that it has a procedural attachment, and answer that particular predicate by looking at the interpretation status of the control program. This kind of has a nice property that this predicate is actually properly counted, and we don't have multiple representations, and it's the best representation we can get because the robot actually uses it for executing its actions itself. It was method 2 that I have already talked a little bit about it. So basically executing underspecified actions, in particular actions with specific effects. So here, in order to flesh out an action, put the pancake mix away. So we have an action specification, perform an action of the type put away. And the object is the pancake mix. And for the destination, we have certain constraints. So we want to put it at a location on the counter, which is stable, reachable, and visible, and not hindering the future activity of pancake making. So this kind of action specification is then translated into a Rollo query, and so we basically go through the different predicates. So we create a set of poses of objects on the counter, take particular member, check the pose, do a physical simulation to check whether it's stable. So in this case it's not stable because it has moved. And then we backtrack until we get these particular places. So in this way, so we have a specific inference method that allows us to actually specialize vague action instructions in ways that are in a realistic way executable on the board. So now we come to another inference method, which is in some way kind of from the inference task very similar to the one we had. And this is basically, but the difference is that now our control decision is actually a persistent object in the control program. So what we are doing now is we want to say the robot should go to a place where it can pick up the object successfully. And the reason we want to have these kinds of things as a persistent object rather than an instantaneous decision is that we want to give the robot in the beginning of the task pick up the object from the table, but at that moment the robot doesn't know what is on the table. And then it actually should, but it still has to know the place where it should go. But when it goes towards its expected place, it gets additional evidences and it has to revise the decision on the fly. So here we have an example how that goes. So the robot is entering the room. It now sees the table. It computes places from which the object can be picked up. At the moment, the position estimate is still very inaccurate, which means that the places are still vague. But as it comes closer, it becomes more accurate. The places come more specific, and then it notices that there are actually two objects on the table. And here it notices that kind of the original place was blocked by an obstacle. So we have a control decision which is kind of constantly updated according to the evidence that the robot gets during planned execution. And it picks it up, goes around in order to pick the second. So this is kind of basically decisions are here commitments to an action parameterization based on the evidence of the robot, but the evidence actually changes over time. So in order to realize that representation, so we basically hardwired that in the control system. So we learned from experience in a simulation environment. So we had trials where we tried to pick up the objects at different places, and some of them worked, here didn't work. So you get positive and negative examples. So for one person, we have that, and if we vary the position of the objects on the table, we get that. And we learned that classification boundaries with the support vector machine, and have for every place essentially the back projected the place from which it can be picked up. So if at execution time we get a rough position and estimate, we simply sample positions of the object from that position, back project the place from which it can be picked up, and if we add these 0, 1 places, we get something that looks like a Gaussian representation. And here we see how that representation can actually be updated at execution time, and how that is affected by inaccuracy of the robot's localization and the robot's localization of it. Okay, the last inference method I want to talk about is if we are now looking at inferences that look kind of more comprehensively in the future. So in artificial intelligence, the problem of planned projection. So again, in artificial intelligence, the problem is typically formulated that you have a set of causal models of actions, and you have an initial state, and you have an action sequence, and you project using that abstract models of actions into the future. And you run into things like the frame problem and all kinds of very problematic representation issues. And I think that one of the reasons is that for projection it's kind of dangerous to abstract away from the concrete situation. So we are doing projection somewhat different. So we take the logical specification of the situation, but then we translate that logical specification into a physical simulation problem. And we take a physical simulator, ODA-based, in order to run the simulation, and we collect all the log data from that simulation. But later we have, again, roller predicates, which kind of translate the log data of the simulation into a timeline representation. Okay, so here's how it goes. We start this simulator, so the robot would actually do that when it learns performing complex actions. Note this particular scenario, so which is essentially the belief state of the robot. And then we run the plan of making the pancakes. And so one of the actions that is critical in terms of pancake making is pouring the pancake mix onto the oven. And in that particular case, so the effect really depends on the height and on the viscosity of the object. So because the robot can't know that, it actually executes the actions with different parameterization and looks what is happening in simulation. So in some of the simulations, it spills pancake mix, in others it's working fine. So here, pancake is poured correctly, and then it actually flips it. And so here we have different scenarios where we actually have different effects depending on the force we use for pushing the spatula and the angle of the pancake. So in some of the cases the pancake is folded, and in others the pancake is pushed off, in others might stick on the spatula, and so on. But again, so even though we are doing that as a simulation, that the result of that simulation is actually a logic knowledge-based timeline. And we can vary what has happened in this scenario very much like we can do in classical AI temporal projects. But the thing to notice is that in our case, we don't run into many problems that AI projection is running into. For instance, how basically concurrent effects of actions are actually interfering with each other. And the reason we are not running into these problems is that we are doing the simulation at a very fine-grained level. And in each of the iterations, we can simply execute the laws of physics, and because we are so fine-grained, we don't run into those problems.
No, it's okay.
Okay.
Just continue.
So I will basically look at the last inference method that I want to talk about today. And again, it's an inference method that we find to be extremely important. And it's what we call Bayesian cognitive robotics. So the idea here is that we want to run our robot control systems for days and perform the fetch and delivery tasks, say, for a week, and 3 hours every day with a robot picking up objects from different containers, putting them at different places. And so associated with these control programs, we want to have an automaton model of the system, which basically contains the goal structure of our robot system. And the robot should actually log its execution data and integrate it to that automaton, which is basically a rational reconstruction of what is happening. So it gets the log data segmented by the automaton, and then what we are doing is we want to learn a joint probability distribution over all these log data. And joint probability distributions are theoretically an extremely powerful representation framework, because once we have these joint probability distributions, we can actually ask every representation unit we have in that joint probability, what is the value distribution for that object, given any evidence that we have. The problem here is that we actually need joint probability distributions over first order representation. So we basically, so if we have a thing like a hybrid automaton that has jump conditions, and the jump conditions, whether an action actually succeeds or fails, depends on the situation, and the situation has to be described in first order expression. So we are working on kind of how can we actually learn such joint probability distributions over hybrid automaton models over these activities. But if we have such a joint probability distribution, so we could do all kinds of inference patterns that would be very useful for the robot. So for instance, we could do prediction. So what is the probability that the task for a particular object in a particular situation is successful, given that we intend to apply class type side from sideways right, that the object is a cup, that relative orientation of the cup is such, so given a particular situation. Or what is the probability that a particular class is successful, given that we had an earlier successful class in previous situation. We can also do evaluation of alternatives. So what is the probability that the robot actually has performed a task of a particular type, given that the task was successful in a particular situation? Or we can do diagnosis, namely we can look at what is the probability that the localization quality is poor, given that a particular task was not successful in a particular. So if we really can manage to have joint probability distributions over complete log data, and we can actually collect log data over long periods of time, and that might be a way to at least get some of the common sense knowledge on a way in the robot that is heavily based on experiential data. Go to the conclusion. Okay, so I just want to, as a conclusion, I want to point out that the main principles that I wanted to highlight in that talk. So the first principle was that if we really want to build robot control programs that can successfully perform human-scale, everyday manipulation tasks, I think we have to go for perception-guided, concurrent, reactive control programs. So the programs have to specify how the robot is respond asynchronously to sensory inputs and failures in order to accomplish its goal. So anything that is a simpler language will not get the flexibility, robustness that we need. So if we want to make the robot more competent, cognitive if you wish, so kind of one important way of doing it is that we enable it that it can reason about control decisions and action parameterization. So that will allow us to actually write in the program, do the appropriate action, do the appropriate action parameterization, and the system will be able at execution time to actually flesh out what that means in that particular situation. And the third component is, even if we have these very expressive control programs, so we have to represent them as semantically interpretable action plans so that the robot can explicitly represent its goal and monitor them, reason about action execution, and explain what it has done, and learn models based on the data that have been gotten. So just finding that. So the research here is supported by the Excellence Cluster Beetz in Munich. By Uni started a European project called EUCogIII, which basically takes many of these questions and actually looks into them very deeply and tries to flesh out the computation principles and underline how those things could be done on real robots and on other projects, namely Safari and EUCogIII. Again, like in the first task, almost all code that I was talking about is available open source in our repository, and if you are interested in our work, you can look at our website. So thanks a lot for your attention.
Okay, thank you very much for an inspiring talk. So I think we have about half an hour for open discussion. Yes, over there.
Can we have a portable microphone? And is there someone else who would be willing to? Yeah, thank you.
So thank you for the nice talk and also for many nice leaders. So you showed us, you talked about many forms of learning within your system, and my question is, do you have also any mechanisms to learn new predicates to decide, okay, my pro database is a predicate, I don't know how to do this task now, I need a new predicate and learn it autonomously as much as possible?
I think that will be part of the case. We are not looking into that right now. So I talked about the high-level part and about the human-scale tasks and activity. I think so. In a complete system, there would be that developmental robotics part, where you actually co-develop procedures and data structures, and where you would also come up with new predicates. The reason why I find that pragmatic, realistic approach is, so we are thinking about, if you really want to equip a robot with that kind of knowledge, we need about, so there might be about 200 action verbs where we need plans for, where we need knowledge bases for, and the top 15 predicates account for about half of the actions in recipes, and for that kind of thing, I think we could make up the predicates that we need also on a programming manner. And this is basically where we are going, but that's obviously because we want to look at these at a high performance immediately and at these very complex tasks. So we kind of, but we would actually expect that we can grow together with developmental robotics, that these kind of things can be developed out of developmental techniques.
Okay, thank you. So first back there.
Okay, thank you. Thank you for a very interesting talk. So my question is related to the previous one. So my point of view is just a bit different. You said that their atomic actions are predefined, but do you see some role of learning or adaptation also for the atomic actions, even if they are predefined?
Yes, so I guess, yes, totally. So I mean, the thing is more that we have to kind of try to do some of the assumptions and some of the, because kind of the whole problem is too complex. But again, I would expect that fields are actually going together, and so there's always a question. I mean, even if you're looking at this kind of recipe, you don't have the tool that you want, and you kind of need to actually improvise and see what kind of action or how would I adapt the action to actually make it work with that kind of tool. It's part of the game. We don't have the resources to look into that, so we hope for others to actually kind of come together with us